Oops, it's not what I meant to do. All right, looking at other aromatic compounds, let's take a look at the rules for aromatic compounds. It says aromatic compounds fulfill two criteria. So number one, we have a fully conjugated ring with overlapping p orbitals, and we have to have an odd number of electron pairs. So it has to satisfy Huckel's rule, odd number of electrons pair, or 4n plus 2 total pi electrons. Okay, and if we have a compound that's anti-aromatic, that's going to fulfill two criteria. We're going to have a fully conjugated ring with overlapping p orbitals, good, and we're going to have an even number of electron pairs, where it meets the 4n rule, where n could be any integer, 0, 1, 2, 3, 4. Let me give you an example of a compound that's anti-aromatic. In fact, I don't even know if this compound has ever been isolated. If you take cyclopentadiene and you make a cation of it, right, then this would be sp2 hybridized, because we know that a carbocation is sp2, and every other carbon in here is sp2. So we have a continuously overlapping system of p orbitals, and it's got 4 pi electrons. And so there we go. It's got a continuously overlapping system of p orbitals, and we have 4n electrons, and therefore this would be anti-aromatic. So I'll redraw the compound here. So if I have this compound like this is anti-aromatic. And again, very few anti-aromatic compounds out there. All right. If a compound fills the first criterion, it would be non-aromatic. Let's say, for example, if you have this compound, let's just say you have cyclopentadiene, like this. Well, this is an sp3 hybridized carbon. Therefore, you do not have a continuously overlapping system of p orbitals. And so this compound would be non-aromatic. All right. Well, let's talk about annulenes. And annulenes are rings that are just completely conjugated. So double, single, double, single, double, single. And annulenes can be aromatic, anti-aromatic, or non-aromatic, depending on the annulene. Now, if we have 6-annulene, well, that's benzene. And we know that that is a planar compound. It has a continuously overlapping system of p orbitals. It satisfies 4n plus 2, where n is equal to 1, so that's good. If we have 10-annulene, however, you probably notice that you have a hydrogen here that's kind of like sticking in the ring, and you have another hydrogen here that's kind of sticking in the ring. And what happens is that causes 10-annulene to be non-planar. So non-planar, it pushes the ring out of planarity, is what we say, and therefore it is non-aromatic because it doesn't have a continuously overlapping system of p orbitals, even though it has a Huckel number of electrons, 4n plus 2, where n is equal to 2. Still doesn't satisfy it. Now, 14-annulene is kind of somewhere in a gray area, really, because you've got a hydrogen here, you've got another one here, you've got another one here, and another one here. And you might be thinking, well, that's just going to push the ring out of planarity. However, the ring is so big that the deviation from planarity isn't all that great. And so we say that 14-annulene is somewhat aromatic. So you could call it aromatic. In fact, I would. If I asked you this question, I would just say, just call it aromatic. And we'll put here, since deviation from planarity is not great. Okay, it's not that non-planar. And then if you get to 18-annulene, for example, so then you'd have 4n plus 2, where n is equal to 4. So 18-annulene, that would be aromatic because it's so big that it's not going to affect the planarity of it at all. Let's go back to this 5-membered ring thing and a frost circle. It says that an aromatic ring can contain a carbanion. So we could have a carbon with a negative charge, and we can have a carbocation in an aromatic ring. Well, let's take a look. If we have a 5-membered ring, and we've got 3 bonding molecular orbitals. If we had a total of 1, 2, 3, 4, 5, 6 electrons in here, then we would have an aromatic compound. We could have an aromatic compound. So how would you do this? Well, what if you took cyclopentadiene, I'll just draw on these 2 hydrogens for instructional purposes. Obviously, you have some here as well. I'm not going to draw those in. But if you were to remove a proton from this, then you'd be left over with this, where you would have a pair of electrons here, and you would have a cyclopentadienyl anion. And you could draw resonance structures for this cyclopentadienyl anion because you have an allylic lone pair. And here we have all of the resonance structures drawn for the cyclopentadienyl anion. And it says here that the cyclopentadienyl anion has the lone pair delocalized over all 5 carbon atoms, and it is therefore aromatic. Now, why would that be? Because instead of the carbanion having sp3 hybridization, it adopts sp2 hybridization. That means that the lone pair would be in a p orbital. So now we've got a continuously overlapping system of p orbitals, and we have, count them. We have 1, 2, 3, 4, 5, 6 electrons in that continuously overlapping system of p orbitals. 1, 2, 3, 4, 5, 6. We have a closed shell electron configuration for the cyclopentadienyl anion, and therefore it is aromatic. That explains why, even though this is just a regular old sp3 hybridized carbon-hydrogen bond, it doesn't have a pK of 50. It's got a pK of 16. It's got this super low pKa. Well, why would that be? Because it's highly acidic. Why would that be? Because if you deprotonate it, you go from something that is non-aromatic to something that is aromatic. And that is the driving force behind cyclopentadiene being a relatively acidic compound compared to, an alkane, let's say. Now, what about a 7-membered ring? Same thing applies. If we had a 7-membered ring and we had a closed shell electron configuration, meaning we had 6 electrons in the bonding molecular orbitals, well, what if one of the carbons had an empty p orbital? What do I mean? Look, what if you had this? You had a 7-membered ring, and then you alternated double, single, double, single, double, single like this. What if this carbon here, what if it was a carbocation? Then it would be sp2 hybridized, and you'd have a continuously overlapping system of p orbitals. Everything has a p orbital on it, and you've got a Huckel number of electrons, right? You've got 1, 2, 3, 4, 5, 6 pi electrons. So this should be aromatic, and we call that, get this name, the tropylium cation. And the tropylium cation has 7 resonance structures, all of which are shown here. And based on the Frost circle and the requirements for a closed shell electron configuration, we've shown that the tropylium cation is a aromatic compound. Now, sometimes if you Google the tropylium cation, sometimes you'll see it drawn like this. Don't do it. You can draw a resonance contributor, but every once in a while you'll see it drawn like this with a positive charge in the center. I don't like that. I like to just draw a resonance contributor and move on with my life. I find that much simpler. So there you go. Those are 2 specific ions that I want you to know. I want you to know the cyclopentadienyl anion, and I want you to know the tropylium cation. Now let's get into aromatic heterocycles. If you've looked at the structures, go ahead.
Can I ask a question? Are carbocations and carbanions always sp2 hybridized?
No, absolutely not. It depends on the situation. So if you have a compound where, a carbocation is always sp2 hybridized. There's no debate on that, okay? Like, let's say you have, if you have a methyl cation, okay, that you made in the mass spec or something, right? That's sp2, okay? There's no arguing that. But let's say you had, I don't know, let's say you had something like, this, and then you have 3 protons on here on acetone, and let's say you deprotonate that, you lose H plus, then you form, this, okay? So like this. So we have 1, 2, 3, 4 regions of electron density, right? 1, 2, 3, 4, and therefore you would say that this is sp3 hybridized. The orbital where that lone pair resides is an sp3 hybrid orbital, the way that I have it drawn here. I mean, we could make it simpler than this. Why don't we just make it butane? Okay, if you're talking about butyllithium or something. So 1, 2, 3, 1, 2, 3, 4. So let's just make it even simpler. We'll just make it a butane carbanion like that. So what's happening here is that normally every time we looked at a carbanion in this class, it was sp3 hybridized. But now what we're saying is, if this lone pair goes into a p orbital, if this carbon adopts an sp2 hybridization, then we do have a continuously overlapping system of p orbitals, which allows this to be aromatic. If this carbanion didn't adopt sp2 hybridization, it would be sp3, and then it would be non-aromatic. But remember, aromatic means stable, and a compound will do what it has to do to adopt aromatic stability. And so the carbon will change its hybridization from sp3 to sp2. Does that help a little bit?
Yeah, that makes sense. Thank you.
Okay, yeah. All right, so let's take a look at some heteroatoms. And Caitlin, I think this will clear it up even more. We'll see a bunch more examples in here. Let's talk about pyridine and pyrrole. 2 aromatic compounds, but for very different reasons. And if you're like, oh, fiddlesticks, why would it be different reasons? Well, it's very different reasons why these 2 compounds are aromatic. In fact, the lone pair on the nitrogen of pyridine is localized. It's not involved in resonance. We went over this in chapter 1 of Organic Chemistry 1. However, the lone pair in pyrrole is delocalized, and it is participating in resonance, and it is part of what causes the compound to be aromatic. Let me show you why. If we look at pyridine, you see that the nitrogen already has a pi bond here between the nitrogen and the adjacent carbon. That means the nitrogen already has a p orbital on it. So in pyridine, we already have a system of overlapping p orbitals, and thus, since the nitrogen is surrounded by 1, 2, 3 regions of electron density, it's sp2 hybridized, but the p orbital is already used to make this pi bond. That means that this lone pair is in an sp2 hybridized orbital. Now, if I was to give you the nitrogen in ammonia, Caitlin, if I said, here's ammonia, and I said, what's the hybridization of this nitrogen? You would say it's sp3. If you look at this nitrogen, it looks like it's surrounded by 1, 2, 3, 4 regions of electron density. It should be sp3 hybridized, but it's not. It's sp2. Why would that be? The reason why the lone pair on that nitrogen is in a p orbital and why this nitrogen adopts an sp2 hybridization is because if we have a p orbital on here, which of course comes from the fact that this nitrogen is sp2 hybridized, then we get a continuously overlapping system of p orbitals, and we have a Huckel number of electrons in that continuously overlapping system, which causes pyrrole to go from something that would be non-aromatic to something that is aromatic. And so the lone pair on the nitrogen in pyridine is not participating in aromaticity, whereas the lone pair in pyrrole is necessary for aromaticity. And that's why pyridine is a good base. It's an electron donor, whereas pyrrole isn't basic at all. It's a crummy base. It doesn't want to donate this pair of electrons because it needs them for the compound to be aromatic. Check it out. What happens? I already covered all this. So what happens if you protonate pyridine? If you protonate pyridine, you get something with a pK of around 5. Okay, this is called a pyridinium cation. So pyridinium ion. And pyridinium is still aromatic. You've got the continuously overlapping system of p orbitals. You have a Huckel number. But what happens if you protonate pyrrole? Pyrrole is not basic at all. You end up making this pyrrole cation, the protonated form of pyrrole. The name escapes me at the moment, but you see that it's much more acidic. It's what, 10,000 times more acidic than pyridinium is. Why? Because this thing is saying, I don't want this proton. Now that I've got this, I'm non-aromatic. I want to lose this thing big time, because then when I do, I become aromatic. Aromatic. And that is why this is just so acidic. Give me a thumbs up if that makes some sense to you. And stop me if you have a question. Okay, cool. Yeah. Now, I know we don't spend a lot of time looking at electrostatic potential maps in organic chemistry in this class, but let's just take a gander here. It says the difference in electron density can also be observed by viewing the EPMs, or the electrostatic potential maps. And these two are on the same slide, so we can compare them. But you see that the lone pair on the nitrogen, which is represented by the orange coloring, is just, it's just stuck in one spot. It's not going anywhere. It's like, I'm open for business, Whereas if you look at the orange coloring in pyrrole, you see it's everywhere. Why? Because it's delocalized throughout the entire dang ring. There you go. So pyrrole, not a strong base, or not basic, I should say, whereas pyridine is basic. Pretty neat, huh? Okay, well, let's try some practice problems. And some of these are easier than others, but let's try and muscle our way through them. It just says determine whether each of the following compounds is aromatic, non-aromatic, or anti-aromatic. Let's take a look at the first one. This is a cyclopropenyl anion, this one here. All right. So this compound, if we have our ring, and if we put this lone pair in an sp2, or if we put this carbon as being sp2 hybridized, so we have this lone pair in a p orbital, and we have a p orbital here and a p orbital here, then we have a continuously overlapping system of p orbitals. However, we have 4n electrons, 1, 2, 3, 4, 4n, where n is equal to 1. Therefore, since this compound is super flat, there's no way for it to get out of being planar. This compound becomes anti-aromatic. So this is an anti-aromatic compound. Whereas here, in the next compound, we have the cyclopropenyl cation, Now, if we have our sp2 hybridized carbon here, and we have another one here and another one here, then these orbitals all overlap. We have a continuously overlapping system of p orbitals. But now we have a 4n plus 2, where n is equal to 0, because we have the 2 pi electrons. And so this compound would be aromatic. Moving on to the next one, I went over this one with you already. So we have a p orbital here on this carbocation. We have a p orbital here. We have them all the way around the ring. And so we have a continuously overlapping system of p orbitals. And we have 4n, where n is equal to 1. And so this would be anti-aromatic. And what about the last one? Does anybody have an idea about the last one? Would this be aromatic or anti-aromatic? Or non-aromatic?
Is it anti?
It's not anti, because if we have these electrons in a p orbital, then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pairs of electrons in a continuously overlapping system of p orbitals. So we have 4n plus 2, where n is equal to 2, right? 4 times 2 is 8, plus 2 gives you 10 electrons. So we have 10 electrons in the ring, and we have a continuously overlapping system of p orbitals. Therefore, it's a Huckel number, and this compound would be aromatic, like that. Okay, let's try a couple more.
So in those first two examples you did, can you
Uh-huh.
explain which electrons are you counting to see if it has 4n plus 2?
So in the first one, I'm counting these 2 electrons and these 2 electrons. So that makes a total of 4 electrons, 2 in the lone pair, 2 in the pi bond, 4n when n is equal to 1. When n is equal to 1, 4 times 1 gives you 4. So that would be a non-Huckel number. That's a 4n number, and therefore that renders this anti-aromatic. If you go to the next one, so here I'm only counting this pair of electrons, 4n plus 2, where n is equal to 0. 4 times 0 is 0, plus 2 gives you 2. And so that would make this an aromatic compound.
So you count all the electrons that are in p orbitals?
Exactly.
Okay, thank you.
No problem. No problem at all. Let's try some other ones. For this one, it says, for each of the following compounds, determine which, if any, lone pairs are participating in aromaticity. So let's take a look. Okay, let's start with this first compound here. So we've got a pair of electrons here, a pair of electrons here that are in pi bonds. Now, if we were to put one of these lone pairs in a p orbital, what would we have? If those were in a p orbital, then we would have a continuously overlapping system of p orbitals, and we would have how many electrons in those p orbitals? Let's count. We'd have 1, 2, 3, 4, 5, 6. Well, that happens to be a Huckel number. So I'm just going to put a circle around these. So we have 4n plus 2, where n is equal to 1, and therefore this would be an aromatic compound. So the question asks us, determine which, if any, of the lone pairs are participating in aromaticity. And so the oxygen in this ring, one of the lone pairs is participating in aromaticity. It doesn't matter which one you circle, but one of them is. If we go to the next compound, it's going to be the exact same rationale. You've got a pair of electrons here, pair of electrons here, and then we've got a lone pair here and a lone pair here. So if I put one of those lone pairs in a p orbital, then I would have a continuously overlapping system of p orbitals, and I would have a Huckel number of electrons, 4n plus 2, where n is equal to 1. And so this would be an aromatic, that would be an aromatic compound. If we look at the next one, what about this one? Now, what's the hybridization of this nitrogen? Is it sp2 or is it sp3? If it was sp2, then this lone pair would be in a p orbital. Then you'd have 1, 2, 3, 4, 5, 6, 7, 8 electrons in the ring. You'd have a continuously overlapping system of p orbitals. That would make the compound anti-aromatic. And so in order for this compound to avoid becoming anti-aromatic, the nitrogen adopts an sp3 hybridization. So sp3, to avoid becoming or becoming anti-aromatic. Okay. The next one, we have a nitrogen with a lone pair and a sulfur with 2 lone pairs. Could this be an aromatic compound? Well, remember something that we learned way back in Organic Chemistry 1. If you have a nitrogen, and we saw this with pyridine, if you have a nitrogen that has, right, if the nitrogen has a lone pair and a double bond, both of them can't be participating in resonance. And therefore, the lone pair on this nitrogen here, this is localized. that is not participating in resonance whatsoever. But we know that the nitrogen is surrounded by 1, 2, 3 regions of electron density. Therefore, it is sp2 hybridized. And also, we see that that it's got a pi bond on it already, so it does have an unhybridized p orbital. That's how it made this pi bond. So that means we've got p orbitals here, 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 here. If we put one of those lone pairs in a p orbital, then we would have a continuously overlapping system of p orbitals, and we would have an aromatic compound. And so the answer is one of those lone pairs on the sulfur is going to participate in aromaticity, and then you would have 4n plus 2, where n is equal to 1, and this would be aromatic. And for the last one, could anybody tell me, would the last one be aromatic or anti-aromatic or non-aromatic? Do we have a continuously overlapping system of p orbitals? We have a p orbital here, 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 here. Now the oxygen is surrounded by 1, 2, 3 regions of electron density. Therefore, the oxygen is sp2 hybridized. And it's already got a p orbital that's making this pi bond here. So we do have a continuously overlapping system of p orbitals. We have 6 electrons in the ring. Therefore, we have 4n plus 2. And so where n is equal to 1. And so this is an aromatic compound, but this lone pair is not participating in aromaticity. It's got nothing to do with the compound being aromatic. All right, there we go. So there's a bunch of examples. Now you're going to have to try some more examples on your own time, which is totally normal. And let's just take a look at the polycyclic aromatic compounds. There's a lot of polycyclic aromatic compounds that are also aromatic. I want you to know the names of these 3. So know these 3 names. Naphthalene. Naphthalene is mothballs. If you've ever smelled mothballs before, then you know what naphthalene smells like. What's cool about naphthalene is that it's a solid at room temperature, and it can be sublimed. It can undergo sublimation into a gas, or be converted into a gas directly, which is the process of sublimation. It's an experiment you can do in the lab to purify naphthalene. It's pretty cool. Next, we have anthracene and phenanthrene. We're not really worried about the chemistry of these compounds, but one thing that's pretty interesting about the annulenes is, these polycyclic aromatic compounds. Here you have 10 electrons in a fully conjugated system, and so you have 5 pairs, so that's aromatic. Here you have 14 electrons, so that's 7 pairs in a fully conjugated system. And here you also have 14 electrons, so that's 7 pairs in a fully conjugated system. So these are all aromatic, but something we don't really talk about a lot in this class is how some of the rings in these molecules are more reactive than others. For example, if you try to do substitution reactions on anthracene, this ring is more reactive than the outer rings. That's something that we cover in majors of organic chemistry, but it's not covered in this class, so I wouldn't really worry about it here. And yeah, there's some information here about stabilization energies. I'll just leave that as an FYI for you. And that brings us to not the very last section, but one of the last sections, which deals with reactions at the benzylic position. It won't take us very long to cover this because we've already looked at a few of the reactions that are covered in here. There's only a few new reactions. Do you remember the Jones oxidation that I taught you earlier on in this class? We talked about taking a primary alcohol and oxidizing it with sodium dichromate, sulfuric acid, and water to make a carboxylic acid. Well, if you were to take benzene and just treat it with those conditions, nothing happens. If you take a straight chain alkane and you treat it with those conditions, nothing happens. However, if you have a proton in a benzylic position, you can get a reaction that's really cool. If you're wondering, what the heck is a benzylic position? Okay, we've talked about vinylic positions. So if you have something like this, right, this is the vinylic carbon. This would be the allylic position. Well, if you have an aromatic ring, the position right off of it, that's called a benzylic position. If you have a proton in the benzylic position, one or more, doesn't matter, but you got to have at least one, you get a really cool oxidation. Check this out. We've got two benzylic protons here, and if you treat butylbenzene, this compound, with sodium dichromate, sulfuric acid, and water, it excises all of this portion of the molecule. It's just gone. Okay, it goes into the organic waste, I guess, and you end up oxidizing this carbon to a carboxylic acid, And we're going to do an entire chapter on carboxylic acids, where we're going to look at lots of cool chemistry of carboxylic acids. Now, remember, you've got to have at least one proton in that benzylic position in order for the oxidation to occur. If you were to try the same reaction with tert-butylbenzene, there's no proton here, and so it doesn't oxidize. Another option for doing this reaction, as long as you've got at least one benzylic proton, is to do it in two steps. The first step, you treat the compound with potassium permanganate, water, and you heat that up. And in the second step, you treat that with H3O+. And the reason why you have to treat it with acid in the second step is because you don't make a carboxylic acid, you make a carboxylate salt. So this is called a carboxylate salt, like that. And then you have to protonate it. In the last steps, you have to treat it with aqueous acid. So we call this, again, benzylic oxidation. So let's go back here. We call this, where was it here? We call this benzylic oxidation. Very cool chemistry. You can do it in acid, or you can do it as two steps with potassium permanganate in the first step, and then aqueous acid in the second step. Well, do you remember free radical bromination? Something that we looked at earlier on, is we said, okay, well, if you have an alkene and you treat it with NBS, so NBS, you can do bromination in the allylic position so that you'll end up putting a bromine here, like this. This is something that we saw earlier on in the class, allylic. So this would be allylic bromination, like that. Well, we can also do benzylic bromination. If you have a benzylic proton and you treat the compound with N-bromosuccinimide, NBS, and heat, you can do a benzylic bromination. And what's cool is that benzylic bromides, like this, are super useful as synthetic intermediates. They have a lot of cool uses. Let's check out some of those uses. First of all, if you have a tertiary benzylic bromide, it can undergo an SN1. Right, the first step of an SN1 is the loss of leaving group. And in this case, you would end up getting a benzylic carbocation, which is highly stable. Everybody here should be able to draw all the resonance structures of this benzylic carbocation. And then, of course, water can come in the next step as your nucleophile. And I'm not going to draw the entire mechanism. But then after deprotonation, we end up with a tertiary benzylic alcohol. Similarly, if you have, so this is with a tertiary benzylic bromide. If you have a primary benzylic bromide, this compound is just called benzyl bromide. You can treat that with sodium hydroxide, and that will just do an SN2 to give you the alcohol. This is called benzyl alcohol. So benzyl alcohol from benzyl bromide, so SN1 and SN2 reactions. What else can you do? You can do E2 and E1 reactions as well. If you have a tertiary benzylic bromide, you can do an E2 reaction because you've got your alpha carbon, you've got your beta carbon, you've got a proton here, right? Your ethoxide is a base. It can remove the proton and you lose the leaving group in an E2 to make an alkene. And then you end up with something that's even more extensively conjugated, which is cannonine. Similarly, you can take benzyl alcohol and treat it with sulfuric acid and do an E1 reaction. So first you protonate this to make it a good leaving group, and it leaves. And then you end up losing a proton to make a new double bond. And so this opens up a whole bunch of new reactions. We discussed benzylic oxidation. We talked about benzylic bromination. And then once you have a benzyl bromide derivative, you can do SN1 or SN2 reactions. You can do E1, E2 reactions. You can make alcohols. You can make alkenes. And we've already done entire chapters on alcohols and alkenes. So this really opens up Pandora's box of possibilities for reactions. Well, with all that in mind, let's take a look at a question. And it says, what would happen if you were to treat any of these compounds with chromic acid, which you produce in situ from taking sodium dichromate with sulfuric acid and water and mixing them together? What would happen if I was to take toluene and treat it with sodium dichromate, sulfuric acid, and water? Anybody? Could anybody name that compound that you would form? What would the compound be called?
Is it anisole?
It wouldn't be anisole because you'd oxidize this to a carboxylic acid. So let's draw it out. What if I draw the compound out? Could anybody identify this compound here? Very common compound in organic chemistry. This is benzoic acid. So benzoic acid. All right. What about the next one? Now, I'm not going to ask you to name the compound, but how many carboxyl groups would we get if we took this compound? So you could call this meta-ethyl toluene if you wanted to. So you take sodium dichromate, sulfuric acid, and water. Could anybody tell me how many carboxyl groups you would produce in this case?
Would you have two?
Absolutely. You get two of them. Why? Because in the first example, we only had one benzylic position with protons. Now you've got two. You've got benzylic protons here, and therefore you're going to end up with two carboxyl groups. So I'm just going to draw the condensed structure here of the carboxyl group, which looks like this. This is called isophthalic acid. You don't need to know that name. At least I think that's what it's called. Isophthalic acid. And then for the last one, we have benzylic protons here, here, and then we have no benzylic H's. And so if we treat this with sodium dichromate, sulfuric acid, and water, we end up with this interesting compound where we have a carboxyl group here. We have a carboxyl group here, so two carboxylic acids. And then we have, then we have a tert-butyl group here. And there we go. So some neat new compounds.
Just really quick before you move on, Ian. I'm so sorry, but on B, I was just drawing it fully out, and on the right side where the ethyl is, when you would draw the carboxylic acid coming off of that, would you draw it like coming off of the top position, or would you just draw a ketone off of the top position and then put the alcohol at the bottom?
I'm not exactly sure what you're asking, but here I've just drawn a condensed version of it.
Yeah, no, I know what you were doing. I'm just trying to draw it out completely.
You could draw it out like this.
Yes. Okay. Okay.
Yeah.
That's all. That's what I was asking.
Yep. No, there's nothing wrong with that. That's just the full Lewis structure. Yeah. It's all good. If you know what, it's the beauty of organic chemistry, and I know that none of you find anything in organic chemistry probably beautiful on a late Monday afternoon. But what's great about organic chemistry is if it's right, it's right. You know, I can't argue with my students and go on some kind of power trip like, oh, well, you know, I'm right, you're wrong. If the answer's right, it's right. You know, one of the best things about studying science. Nothing about your instructor's opinions. Nobody cares about my opinions. It's just about facts. All right, why don't we take a short break before we get into some more facts about chemistry, and we can just cover the very last section of this chapter. It's a short one. It deals with reduction of benzene, and what's cool about this, we did sodium metal reduction, didn't we, when we were reducing, oh yeah, that's right. We reduced, I don't know, I'm just thinking out loud here, but when we reduced a alkyne to a transalkene. I taught you the radical cation, didn't I? So we did sodium and liquid ammonia, right? But this is the reason I was thinking of that is there's not many times we just look at plain old sodium, but if you look at this reaction, it's one of those reactions where you get to actually play with some sodium. So kind of fun, dangerous chemistry, the birch reduction. So why don't we take a short break and we'll come back and we'll talk about what's called the birch reduction. And it's really the only new reaction in the rest of the chapter. It's the only thing. There's just two little caveats with birch reduction that involve electron withdrawing and electron donating groups. And then the very last section deals with the spectroscopy of aromatic compounds. I mean, are we really skipping this? I would say no, because we covered all this in Organic Chemistry 1. And it's something that I expect you to all be aware of anyhow. I expect you to understand the spectroscopy of aromatic compounds. And so I assigned a couple problems from the book. And I don't mean assigned like for points, but in the suggested practice problems, I put a few problems from this section because I expect you to be able to understand an NMR or an IR that's got an aromatic ring in it. So, yeah. So why don't we take a short break and then we'll come back. We'll talk about the birch reduction. Just got a really neat mechanism. It's very short. And that'll be it. That'll cover the entire chapter. And then when we come back on Wednesday morning, we could just spend the whole time, or at least a good chunk of the morning, practicing. And then we could start up on chapter 18, which is more aromatic chemistry. But that chapter, again, is very hardcore on reactions. It's just reaction after reaction. So, oops, I didn't mean to do that. One more thing I'll tell you, just to pique your interest. And I'm sure, like I said, that no